Hi, my name is Dr.AhMath. Welcome to the course of Biophysics 1. In this lecture, we're going to talk about the action potential. In the beginning of the lecture, I would like to give you a brief description and definition of the action potential. So the action potential is a rapid rise and subsequent fall of the membrane potential across a cellular membrane. If I just look to this definition at the first glance, we don't really understand many things here. So throughout this lecture, we're going to discuss and define many definitions, like what is the potential, what is the membrane potential, what is the polarization of the cells or depolarization of the cells. And I hope that at the end of the lecture, we're going to have much more understanding of this definition of the action potential. At this stage, what we need to know is that the action potentials are really important for our cells. So cells send a signal via action potentials in the neurons, and we can have the action potentials, for example, in the cells of the muscles, which are responsible to the control, to coordinate of a movement of our body. So we can have the action potentials in a muscle cells of our hearts, or we can have the action potentials in the cells of endocrine system, which are responsible, for example, to the release of the insulin. So the action potentials are really important, and we can have them in many types of the cells. So in this lecture, we're going to concentrate on the action potentials, which we can see on the neurons. So this is the picture. So before we start talking about the action potentials, I would like to start with a question actually, what is the potential? In physics, the potential is simply the separation of the charge. And the separation of the charge basically means the amount of the positively and negatively charges in a structure. For example, a battery with a potential 9 volts means that there is a separation of the charge inside the battery. So we're going to better concentrate on the separation of the charge across the cell membranes. So here is basically, so throughout this lecture, we're going to talk about the action potential on the neurons. So, but we can have the action potentials on the muscle cells as well. So this is the cross-section picture of a neuron. And we can here have the positively charged ions of the potassium, for example, across the membrane of a neuron, or we can have the the positively charged sodium ions here again across the membrane, but outside. So the membrane potential is the difference in charge between inside and outside of a neuron. It basically means, hey, so if you have some charge outside and if you have some charge inside, what is basically the difference in the charge? At the rest, when no signal is transmitted, the neuron has a resting potential which is equal to the minus 70 millivolts. If I look to this picture, I can see here the positively charged potassium ions or positively charged sodium ions. And when this negative charge is coming here, so negative membrane potential, it means here that minus 70 millivolts actually means that amount of the charge inside is less than the amount of the charge outside for approximately 70 millivolts. So the membrane potential is the difference in terms of the charge. So if you want, you can just understand this, hey, in terms of, so you can understand the membrane potential in terms of the difference in the number of the ions inside and outside. So if you look here, so we're going to have minus inside and plus outside. It means that we have less ions, less charges inside than outside. So the situation of a cell is called the polarization. So we say that this cell is polarized because we have this minus and plus situation. So minus potential membrane potential inside and positive membrane potential outside. So what I would like to do is I would like to look to this picture from a different perspective. So here we have the so positive membrane potential. Here we have the negative membrane potential, and we have here lots of ions. So for the simplicity, we're going to talk only about the potassium and the sodium ions. So it appears they move in and out across the membranes, and they are going to do this using the spatial ion gates. So there is a spatial ion gate for the potassium, so through which the potassium ions are going to move in and out. And there is a spatial gate for the sodium ions. So through this ion, the sodium ions, so through this gates, the sodium ions are going to move in and out. So at this stage, you need to also know that the concentration of the potassium ions is much more higher inside than outside. It means that the number of the potassium ions inside the cell or inside the cell membrane is much more than the number of the potassium ions outside the cell. At the same time, we have the reverse situation for the sodium ions. So the number of the sodium ions is much more outside than inside. So the concentration of the sodium ions is much more higher outside than inside. So this is important for us because we're going to now talk about the potassium ion channels and sodium ion channels in more details. So let's talk about the potassium ion channels. So the potassium ion channels, so the permeability of the potassium is really important because they basically establish the membrane potential. So this movement of the potassium ions in and outside the cell is basically defining the potential membrane. So we can hear, so as we told before, that the concentration of the potassium ion inside is much more than the concentration of the potassium ions outside the cell. So basically more potassium ions we have inside. So this will lead to the chemical gradient. So the chemical gradient basically means that the concentration of the ions, so inside and outside, are different. So, and since the concentration of the potassium ions inside are more, so they tend to go out. So some of them, they can go out. So at the same time, there is a separation of charge outside and inside the membrane, so outside and inside the cell. So as we told in the beginning, that there are more positively charged particles, so ions, outside the cell than inside. So this will lead to the electrical gradient. And actually, the electrical gradient means that there is a difference in charge outside and inside the cell. So now let's look to the situation. So you've got really high concentration of the ions. So some of them are moving out, right? It means that this chemical gradient is decreasing, right? So you can imagine that you've got really small amount of the potassium ions outside, but much more amount concentration of the potassium ions inside. So some of them are moving. It means that inside the concentration is becoming smaller and outside the concentration becoming higher, right? It means that the difference becoming like smaller. So it means that the chemical gradient is decreasing. But at the same time, so we've got a huge charge, positively charged outside, but small positive charge inside. So that is why their difference is basically negative inside, right? So if even more positively charged potassium ions are going out, then this charge outside is becoming even more, right? So it means that the electrical gradient is increasing. So as chemical gradient is decreasing, the electrical gradient is going to increase. So this combination of the chemical gradient and electrical gradient is called the electrochemical gradient. So this is called the electrochemical gradient. So we are going to have a similar situation for the sodium gates. So we've got again the higher concentration of the sodium ions outside than inside. So this will create the chemical gradient. So some of them will tend to go inside the cell, and at the same time, the separation of the charge outside and inside is creating the electrical gradient. So this combination again is going to create the electrochemical gradient. Electrochemical gradient. So let's look to the p-hat simulation in order to better understand what is going on, and play with this a little bit. So here this is the p-hat simulation. There is a link in the description of the lecture which leads to the simulation. I would just suggest you to just go through this link and try to play with this a bit. So here we can see the potassium gates, and we can see here the sodium ion gates. So we can here see the concentration of the potassium and the sodium. So you can see here that the concentration of the potassium inside is much more higher than the concentration of the potassium outside. And reversely, the concentration of the sodium outside is much more higher outside than inside. So, good. So if you remember in the beginning, we say that the membrane potential at the rest is equal to the minus 70 millivolts. So keeping this minus 70 millivolts is really important. So some of the potassium ions are going out, and some of the sodium ions are going in. So it may change the balance between the ions, between the charges. So the charge potential membrane is going to might change. So we need to keep this balance. So the maintaining the ion balance is very important. So one of the things which can help us to keep the balance of the ions is called the potassium sodium pump. So we say that through this gate, some of the potassium ions are going out, right? And through this gate, some of the sodiums are going in. So potassium sodium pump, what it does is it takes 3 sodium ions inside. They will leave, so they will let them outside the cell, and they take 2 potassium ions from outside, and they will put them inside. So this potassium sodium pump, so put 3 sodium ions outside the cell and 2 potassium ions inside the cell always. So this potassium sodium pump help us to maintain the ion balance. So maintaining the ion balance is again very important. So the sodium potassium pump uses the energy generated by the ATP hydrolysis in order to do this process, in order to maintain the ion balance. And also you need to keep in mind that potassium sodium pump is always keeping, taking out 3 sodium ions and taking in 2 potassium ions. So and this process actually may use from 20 up to 40% of the brain's total energy use. So this maintaining of the sodium, so maintaining this ion balance. So now, if you remember our simulation here, so the p-hat simulation, so we have got the gate, the potassium gate, and the sodium gate, and we have here 2 different types of the gates as well. So I'm curious to know why we actually need them. So let's discuss actually those 2 types of the gates. So we have 2 more gates. We're going to discuss them. So one is called voltage gated sodium channel. So here we have here this voltage gated sodium channel with this little circle here. So again, we say that there is a movement of the ions. So inside and outside, so through some stimulation of the charge, so the charge inside, so the membrane potential inside, which is always minus 70, may increase. So it may come until 55, minus 55 millivolts. So when the charge inside the cell, so the potential membrane inside becomes minus 55 millivolts, so this voltage gated sodium channels are widely open and let in lots of sodium ions. So many sodium ions are going inside the cell through this voltage gated sodium channel. So basically, when this becomes minus 55 millivolts inside, so this voltage gated sodium channels are going to open and they let in lots of sodium ions. It means that the concentration of the charge inside is increasing, right? So the potential membrane, so the membrane potential, sorry, is increasing. So actually, we can link to this here. So this line minus 55 is actually this critical point, because when the membrane potential inside the cell reaches this number minus 55 millivolts, this voltage gated sodium channels are going to open widely and let in the sodium ions go inside the cell. So the membrane potential is increasing inside, and it is going to increase until plus 30 millivolts. So when the membrane potential inside a cell is reaching plus 30, there is another voltage gated channel is going to open. But before we discuss this, we need to discuss one more thing. So now, when the membrane potential inside is increasing and it becomes plus 30, it means that the amount of the charge inside the cell now is more than the amount of the charge outside. So the membrane potential outside becoming minus. So if you remember, we used to have minus and plus. So now they have changed, right? So this process is called the depolarization. So we've got the polarized cell with minus inside and plus outside. So as more sodium ions are going inside these cells through this voltage gated sodium channel, the membrane potential signs are going to change. So this process is called the depolarization. So when the membrane potential inside the cell is reaching plus 30 millivoltage, there is another voltage gated potassium channel. So this is going to open at the plus 30 millivolt. So whenever it opens at the plus 30 millivolts, lots of potassium. So if you remember, there was a huge concentration of the potassium ions inside, right? So many more of them are going to move out. It means that the membrane potential inside the cell is going to decrease. So it's going to decrease. And again, so the inside the cell, say the potential membrane is becoming minus, so usually it becomes minus 70 millivolts, and outside it becoming again plus. So again, in a resting potential is negative inside and positive outside. So as the charge inside is increasing, the charges, so the signs of the membrane potential are changing. It is called the depolarization. As it reaches the plus 30 millivolts, there is another voltage gated potassium channel is going to be opened, and this voltage gated sodium channel is going to be closed at this stage, and lots of potassium ions are going out. This will lead to the original situation again, to the minus inside and plus outside. So this process is called the repolarization. So we've got initially the polarized cell. So as we have changed the sign, so this is called the depolarization. Again, if you change the sign, it becomes, so this process is called the repolarization. So this is actually this process of increasing the membrane potential and rapidly decreasing is called the action potential. And we can see this in the simulations. Let's look to the p-hat simulation one more time. So I'm going to make this a little bit slower. So we are going to stimulate the neuron so that this charge is going to reach, so the membrane potential is going to reach minus 55, and lots of these gates, the voltage gated channels, are going to be opened. So let's look to this. So we have stimulated, so now those gates are going to be open. Lots of sodium ions are going in. Then when it reaches plus 30, lots of potassium ions are going out. Then it becomes again to the normalized situation. So we can look to this using the potential charge here. So this is the charge of the membrane potential. So this is the membrane potential through the time. So what I would like to do is I would like to, again, let's stimulate this one more time. So when we stimulate, those gates are going to be open and let in lots of sodium ions in. And when it reaches plus 30, these gates are going to be open and lots of potassium ions are going out, and it becomes again to the equilibrium situation. So the rapidly increase and decrease of the membrane potential is the action potential. So let's review. So the membrane potential is the difference in charge between inside and outside the cell. So the concentration of the potassium inside is much more higher than the concentration of the potassium outside the cell. Concentration of the sodium ions inside is less than the concentration outside the cell. So we have talked about 5 different types of the channels. There are much more others, but these are the important ones. So the potassium channels lets out and in the potassium ions. The sodium channels lets in and out the sodium ions. Potassium-sodium pump actually lets 3 sodium ions out and 2 potassium ions in always, right? So since the potassium ions are going out using this channel, and the sodium channels, sodium ions are going in through this channel, this pump helps us to keep the balance in terms of the charge ions inside and outside the cell. So the voltage gated sodium channel is the spatial channel which is going to be open when the charge, say the membrane potential, reaches minus 55 and let lots of sodium ions go inside the cell. And the voltage gated potassium channel, it's a spatial channel which is going to be open at the membrane potential value plus 30 millivolt, and let lots of potassium ions to go out from the cell. So let's review what is going to happen. So actually, there is lots of interaction, so movement of the potassium ions and the sodium ions across the membrane. So if lots of ions, more ions are moving out, and lots of ions are moving in, so the membrane potential inside, which is always more or less always is minus 70, may increase. But if they doesn't reach this critical point, minus 55 millivolt in this case, which is called a threshold, then this will be coming to the equilibrium position again because of the sodium potassium pumps. So this will maintain this balance. But if the membrane potential increases until this threshold, until this critical point, minus 55 millivolts, then the voltage gated channels are going to be open and let lots of sodium ions go in. Then when it reaches the plus 30 millivolts, so the voltage gated potassium channels are going to be opened and let lots of potassium ions to go outside the cell. In this situation, the rapidly increase and then subsequent fall of a membrane potential across the cellular membrane is called the axial potential. And this is what we have discussed and what we wanted to understand, and hope that you have much more understanding on this definition now at the end of the lecture.